Everyone, we are Team 6 again, and today we will be discussing our project, Super Frame Rate Resolution. Currently, animators work for very low pay with intensive hours. These factors make creating new works a grueling process. In order to counteract this, our team proposes the use of deep learning techniques to help automate the task, creating artistically beautiful animated movies that touch the lives of everyone that comes across them. Our project utilizes the popular 2016 anime film, Your Name, as the dataset and aims to increase the frame rate by generating more frames in between existing frames, in order to alleviate the number of hand-drawn frames artists would need to make. Frame rate interpolation has been done with variational autoencoder models and generative adversarial networks before, showing promising results. Our work can be considered a re-implementation of a few papers with modifications on existing model structures in order to accomplish the task. In regard to the dataset, we made use of two different resolutions of the movie, 142p and 320p, took samples from a list of unique images from different scenes, then trained each model on the shown number of images. In this slide, we show a couple of examples of our data. Our project approach can be broken down into three parts. First, we modified an existing Beta VAE model architecture in order to be compatible with our targeted image resolutions. Then leveraged the byproduct of training our Beta VAE network to find the different distributions at scene level in the latent space through analysis of KL divergence, followed by finally interpolating frames using the ACAI model. This is how our modified Beta VAE model looks like. It is much deeper when compared to the baseline VAE due to the fact that we had to incorporate it for larger image size. We also had to account for the asymmetrical image by adding outpadding to the deconvolutional layers. In order to detect scene changes automatically, our model makes use of the KL divergence. Within the latent space of our Beta VAE models, each scene would be considered its own Gaussian distribution within the space. Essentially, when the KL divergence value is large between two consecutive frames, we label this as a scene change within the movie. In this slide, we discuss how the ACAI model works. A high-level description of the interpolation pipeline is as follows. First, in order to generate one or more interpolated frames, we take each pair of adjacent frames from the original movie dataset and feed them to the model's encoder. Next, the two latent vectors generated by the encoder are combined linearly to generate one or more intermediate latent vectors. Next, all intermediate latent vectors are then fed to the decoder to generate interpolated images. And finally, we use a discriminator against the generated images to improve their quality. Here we see the results of the image reconstruction using our modified deeper VAE for 320p and 142p resolutions. This is a plot of validation binary cross-entropy loss, which compares our model with the Beta VAE model for different beta values. BCE is indicative of how well the model will be able to perform reconstruction of images. It can be seen that our model is taking longer to converge as compared to the original model, most likely due to the fact that our model is deeper, as it was designed for images of size 142 by 189, whereas the baseline model was designed for 64 by 64. This is a plot comparing KL divergence for different values of beta. KL divergence is indicative of the quality of the latent space, and our model seems to be performing comparable or slightly better when compared to the baseline VAE. The plots that we are presenting are the ones generated for the validation dataset. Our main objective of modifying Beta VAE was to be able to use the latent space of encoded images to identify scene distributions. We first tested this on a small dataset. This graph shows how the mean changes significantly when the scene changes across images. This is a plot of KL divergence between consecutive images in the validation dataset, which has about 14,000 images from about 259 different scenes. Looking at the results from the ACAI model for frame interpolation, we found that the model started to diverge after around 6,000 epochs of training, most likely due to the fact that we trained on only one scene of 128 frames at size 142p. Thus, the model is most likely overfitting to this small dataset. Visually, we can also see from the interpolated frames that the reconstruction quality degrades after around 6,000, 7,000 epochs. The quality of frame interpolation depends on both the autoencoder and the discriminator in the ACAI. Initially, while the team was improving our Beta VAE model, in parallel on a separate task, we tentatively used the autoencoder specified in the ACAI paper for frame interpolation. In the future, we would incorporate our own modified Beta VAE into the ACAI model. And in conclusion, we find that Beta VAE can be used for scene identification with a larger beta value actually improving the reconstruction. Our ACAI model could potentially be used to increase frame rate if trained for longer, And lastly, results from the scene identification can be used to enhance the ACAI model to generate enhanced results.